So our next presenter is David Scarborough.
I assume everyone can see the slides at this point.
Yes. Yeah.
Okay. So this is an unusual venue for us. I guess one that we've kind of become more comfortable with in the last year or so during all this COVID difficulties we've had. But it's more difficult to give these presentations when we can't see the audience. But we'll get through it. So this is going to be a brief overview of the work that's going on at the Combustion Physics Lab here at Auburn. And some of I guess I'd be remiss if I didn't thank the students who helped me with putting some of this together and who are largely responsible for much of the work that's presented here. So the PhD students are Luke Humphreys, Eric Van Horn, Daniel Stubbs, and Ari Goldman. We have a couple of undergraduate students that work with us, and we try to maintain a reasonable number of undergraduates. We'd like more than two, but we try to maintain a reasonable number of undergraduates, both to give them a taste of what goes on in research and a little bit more practical experience, and hopefully even to entice them to come to graduate school. So we're going to talk today about a few things. This is not entirely a comprehensive list, and I'm not going to read through this other than just to highlight that in our lab, we do focus on combustion, but combustion occurs at the intersection of fluid mechanics and heat transfer and chemistry. And in the case of combustion instabilities, we can also throw in the acoustics world as well. So, while we are a combustion laboratory, obviously there's a lot of emphasis on fluid mechanics and acoustics, as well as combustion phenomenology. So what I'm going to do here is just highlight a few things that we're currently working on. And if there's time at the end, I'm going to comment on a few other things that we have or have been working on or plan to. So the first thing I want to talk about is I've got to figure out how to get this. Okay, there we go. First thing I want to talk about is a project we're involved in with NASA on plume surface interactions. And this is a collaboration between myself and Vrishak Raghav, Brian Thoreau, and Toshi Hirabayashi. So we have the fluid mechanics, optical diagnostics, and even planetary sciences represented here. The two graduate students are Daniel Stubbs and Lokesh Silwal. Daniel works for me, and Lokesh primarily works with Dr. Raghav, but they jointly are helping out and basically carrying out this research. So just a brief introduction, the plume surface interaction problem occurs in a lot of different situations, but the one we're concerned with and NASA's concerned with is crater formation and lunar dust blowing, or even in a case of a lander on Mars, what kind of cratering and dust blowing occurs there that might damage equipment or even cause a lander to be destabilized and possibly topple over if it were to settle out in a crater. So there's risk to personnel, there's risk to scientific equipment that's already on the moon, there's risk to the lander itself. And this has been called one of the most important obstacles to man returning to the moon. A number of astronauts were very, I guess, frustrated by the lack of visibility and landing and even just dealing with dust once they were on the surface of the moon. So in any event, we've developed an atmospheric optically accessible experiment to study crater formation and plume surface interaction, and a schematic that is shown over here on the right. Basically, it's an atmospheric facility with glass walls. There's a nozzle that's mounted to a linear traverse, so we can actually simulate both static fire conditions and also what would happen during a descent type phase. So how does the crater formation happen, and what happens to the dust during descent? And to make these measurements, and I guess what's pioneering in this work, and I should point out that there are many other groups that are working generically on the crater formation problem, but I think what's unique about our program is that we're trying to use stereo photogrammetry to measure crater formation and even particle velocities and trajectory in 3 dimensions. So our goal is to measure both the crater depth, radius, and volume evolutions as a function of time for both statically fired nozzles and ultimately descending nozzles. And I should also point out here that this is kind of the first year of this project. We are now working on a subatmospheric pressure facility to be able to do these measurements without the ambient atmosphere around. So as I mentioned, one of the important parts of this is the use of stereo photogrammetry, basically the use of 2 or multiple cameras to be able to reconstruct a 3-dimensional scene and do that at high speeds. So fast enough that we can actually resolve the formation of the crater. And one of the first things that, I guess in the sense of the project, but not one of the first things that we did, was to assess the accuracy. So how accurately can we measure objects or surfaces using the photogrammetry technique? And we did that in a couple of different ways that are shown here. These are actual hardware. These are schematics of the actual hardware. One is a pegboard and one's a crater. We made stereo images and then reconstructed those. You can see the reconstructions at the bottom. And it turns out we're able to very accurately reproduce those objects using the stereo photogrammetry. So moving on from that, here's an example of a crater or a crater formation process. You see at the top there are actual images from the 2 different cameras. We go through a image processing procedure, and ultimately we're able to reconstruct the crater in 3 dimensions. So at the bottom you see a 3-dimensionally reconstructed scene of the crater. And from that, we can then go in there and extract the depth and radius and even volume histories. You can see some plots of those things here. So these are for different nozzle firing elevations above the surface. The first one is the crater depth evolution, and the next one is radius, and the last one is taking the 3D point cloud and generating the crater volume as a function of time. So that's a project that we're very actively involved in. We also, a little out of the ordinary, we're also working on some experimental characterizations of wildland fire. So there's a significant threat to homes and businesses due to wildfires, especially now in the day when we build homes right next to wildland areas. And there are lots of concerns and lots of needs involved here, but the bottom line is that both experimental data is needed for use in models and also just to validate models in general. And so what we're trying to do is use a combination of both traditional and modern optical diagnostics to measure the propagation of these wildfires in a controlled environment. So for example, we use load cells to measure the rate of fuel mass loss, whether there's any residual material left over, thermocouples to measure temperatures, and a gas analyzer to measure emissions from the flames themselves. In addition to that, we can take high speed, or even in this case, we frequently use slower speed diagnostics to measure how rapidly the flame propagates across the surface, the geometry of the flame itself, and even the intensity, the chemiluminescent intensity, which is a measure of the heat release rate. So I'm going to skip over the slide here for interest of time. But the point is we can very accurately get mass loss as a function of time for different fuel loadings. At the bottom, you see a comparison of the actual mass loss rate for different fuel loadings, both measured using load cells and actually calculated from the optical diagnostic data. And so we were able to get a lot of information from that. And one of the things that we found is that at least in the cases that we tested was that primarily the mass loss is due to flaming combustion rather than smoldering combustion. So that's something that we're looking into as well. So I'm going to transition at this point and talk some about in the general area of combustion instabilities. We do and have developed some tools for reduced order modeling tools for predicting combustion instabilities and when a combustor will be unstable and the frequency that it will be unstable at. And one of the big pieces that's missing in those models is understanding the acoustic response of engine components. And so we have a method for measuring the acoustic impedance of insertion elements, as we call them. For example, a fuel air mixer, what we call a swirler in a gas turbine engine, and we're able to measure the resistive and reactive parts of the impedance of those as a function of flow rate through those devices. Similarly, for perforated plates. And in a different series of tests, we worked on another component that it basically is used to measure both to ignite the flame and also to measure the amplitude of the instability in the engine. And I'll just point out the key issue here is that because the pressure transducers are located in standoff tubes, this device has an acoustic response. And so the actual pressure measured by the pressure transducer can be, in this case, as much as twice as high as the actual pressure. And then at other frequencies, you're actually measuring much lower than the actual acoustic pressure. And so understanding the acoustic response of this device is critical to properly diagnosing or measuring the acoustic pressure in the engine during instabilities. We also do a good bit of reduced order modeling. We've developed a model. It looks complicated, but once you plug it into MATLAB, it's not that difficult to use, that is able to predict the nonlinear acoustic response of some certain engine components, things like area contractions, perforated plates, and orifices. And I'll just skip to this slide here. At the bottom left, you see some data for an area contraction, and the model is laid over top of those measurements. And you see we're actually able to do a really good job both in the purely linear acoustic regime and as well at very low flow rates where acoustic nonlinearities dominate the acoustic response of the components. And we're actually using these models and comparing them with data for orifices, as well as the swirler and perforated plate that we saw earlier. So basically what this boils down to is you can identify one parameter like a discharge coefficient or a loss coefficient and apply it in that model, and it'll give you the acoustic response of the component that you're interested in. One other area that we're doing some modeling is in using COMSOL to try to simulate the acoustic response of these components. And so again, just to show you the results here, after significant work on developing the methodology, you can see at the right, we have good agreement between the what we call reference results or well-established results and the results that we obtain from COMSOL. And the advantage of this clearly is we can explore regimes with COMSOL that we can't do experimentally, and even explore components that we may not be able to work on experimentally. So one last area, and I'll wrap this up. This is an area that new graduate students have been working with me on, and that is looking into additive manufacturing for rocket engine, both liquid rocket and rotating detonation engines. And in particular, we're looking at how to develop and evaluate quickly these high performance injectors that are designed to be resistive to pressure oscillations in the engine, while at the same time giving desirable combustion and spray pattern. So we intend here to be using some stereographic and planoptic imaging techniques to look at the spray patterns produced by these injectors. And true to form, there isn't a lot of time to talk about anything else, so I'll go ahead and stop here. And if there's any questions, I'll be happy to entertain them.
Thank you, David. So we have a couple minutes for questions if anyone has any.
Dr. Scarborough, I was just curious when you're talking about lunar landers and obviously the dust problem on descent. Has there been any research as to whether the dust properties are different at different locations on the moon?
Well, that's not my area of expertise, but I think the answer is they are. We believe they are. Obviously, in some places, what we call dust is deeper than it is in other locations. There are, regions where, very within, I guess, a few inches of the surface, it reaches a more granular and compacted region. But that's actually why we have Toshi on board, is to help us out with questions like that.
Well, NASA's doing a lot of work on lunar dust because of the Gateway program.
Absolutely.
Now, whether or not they're looking at variability across the surface, I don't know, but I do know there's quite a bit of work going on in that area.
Yep.
Well, we're definitely excited to be involved with the next generation of some of that stuff. So let's thank all three speakers. And I appreciate everyone being out here this afternoon, and our next session will be in 20 minutes. So
I just want to make sure you tell Roy we were sorry not to see his smiling face live on the show.
I'll pass that on to him for sure.
Okay.
All right, thanks.